Can everyone see the slides well? Yeah?
Yeah.
Yes.
Okay, great. So thanks everyone for coming. This has been kind of a pet project of mine for the last year in some way or another, getting it into OMFIT for the past maybe 3 or 4 months. So I'm just going to do an introduction with some motivation. A lot of it is, we have some people here that are M3D-C1 experts. We have some people here that are OMFIT experts. So I'm going to give a brief overview of both and why we went with this. So for some people, some of the slides might be very basic, but might not be the case for others. So M3D-C1 is an extended MHD solver. It's a fully three-dimensional code with all sorts of different dispersive terms. Includes 2 fluid effects, optionally. Has linear and nonlinear modes, and uses a high-order C1 continuous finite element representation on an adapted mesh to whatever equilibrium you're using. And I just have the equations here for completeness. So most of my work has been linear runs. And linear M3D-C1 is a very, when you're doing an actual calculation, it's very fast. It's solving linear equations, and so runs take on the order of minutes to complete. Maybe tens of minutes, something like that. But actually doing the setup for those runs from a new equilibrium that you have, that can be very time intensive. So simulations typically begin from some kinetic equilibrium reconstruction. And then you have to pre-process whatever data you're given into formats that M3D-C1 can read, including getting coil currents if you're doing resistive wall calculations where the colloidal field coils might be inside the domain. You have to extrapolate whatever kinetic profiles you have, which typically only go out to the separatrix. You have to extrapolate those to the open field line region so that the density and temperature get low enough out there so that it's properly modeled as a vacuum. And then you have to do multiple runs before you can actually do your calculation. Typically, when I run, I do a run where I'm just mapping the equilibrium that I've received to the mesh in M3D-C1, and then I recompute the equilibrium on that mesh, and then I compare the shape to make sure that I'm getting a good match between the two. And then you have to adapt the mesh to that equilibrium that you have. And so you wind up doing 3 or 4 runs even before you get to do a calculation. If something goes wrong, you have to change the input parameters and start all over. Only after you do all this and you have a good adapted mesh to your equilibrium can you actually do a meaningful physics simulation. When you do this manually and serially, this can, for me, it could take hours of babysitting and tuning parameters and everything, and it could be prone to error if you get confused of what folder is where and everything. So last year I started making this script that I called AutoC1 that simplifies the running of linear M3D-C1. It's a command line based Python script that starts with a kinetic equilibrium, and it does all the steps that I described in the last slide for you. And in order to get to doing the linear calculation that you want to do. If something goes wrong, you can restart it at any step, tweak a parameter and restart from there. And it could be interactive, so you could have it give you options that print out to the command line that you respond to, or you can just automate it using assumed default parameters. It uses existing templates that I made for different machines, right now for D3D and ASDEX mostly, but I have an NSTX one under construction that I think needs some tweaking, but it wouldn't be too hard to get that up and running. And it assumes default input parameters in the C1 input file, which is the monolithic Fortran name list that M3D-C1 reads in for all its options. The defaults don't always work, and so you need to have some level of expertise in using M3D-C1 to know how if something goes wrong, what you're supposed to change. then allows you to select an arbitrary number of linear calculations that you want to perform in a given equilibrium, and then you just hit go, and it does everything that you need to do to complete it. So this is all up on GitHub. If you wanted to play around with just the command line, you could download it. But I've also interfaced it with OMFIT. So OMFIT is the one modeling framework for integrated tasks. This is kind of just an overview slide of what OMFIT is supposed to be. It's centered around the OMFIT tree, which is a hierarchical, self-descriptive data structure, and it allows you to load in multiple modules at a time and be able to exchange information between them so that you can couple codes together very easily. It's built purely in Python, so it's easy to install on any platform, including your laptop, and then supports remote and parallel execution of code. So you can be running OMFIT on your laptop and sending jobs off to NERSC or wherever you want to send it to. And then it's all you write all your scripts in Python, and that allows you to link them together. And the idea is that you have your code that you work on, and then you just write wrappers on top of it that OMFIT uses to run your code however you want. So you maintain control of your code and however you want the input and output files to work and how you want it to execute. And you just have it. You just have stuff in OMFIT on top of that allows it to link to everything else. It has often uses graphical user interfaces, and it has simple API for making a GUI within OMFIT, and you can access experimental data through it, and has a very collaborative development, bottom-up development environment. So people are often working together to accomplish a task. And so we'll get into using OMFIT in a little bit. But just to kind of show you what it looks like, it has this overall GUI that has the OMFIT tree on one side, which contains all the modules and data structures, and everything that you're storing there is contained over here. I think it's all based on top of a Python dictionary, right? Mm-hmm. Yeah. So it's essentially just a graphic representation of a Python dictionary. But then it has a command box where you can type simple commands if you want to test something out. That can access everything that's over here, as a console that's printing things out either from what you're executing in the command box or scripts that you might be executing from the tree. So there's now an M3D-C1. Unfortunately, it doesn't have the dash like the code does, but the module is called M3D-C1, and it runs auto C1 through a GUI. So this allows the user within the GUI to select any equilibrium and profile files that you have. It allows you to extend the profile interactively so you can get a good profile that you want to input. You can modify the C1 input file however you want. And then you select whatever calculations you want to perform. And then you just click a button that says Run Auto C1, and it sends it off to whatever server you wanted it to run on. And does the calculation completely in automated fashion from there. You can restart new calculations in that directory once you're done. And then recently I've implemented a way of doing post-processing within the GUI as well. What's nice about this is, in addition to just being useful for running M3D-C1, this allows you to easily link M3D-C1 to other OMFIT modules. For example, if someone's using the kinetic EFIT module to make equilibrium reconstructions on D3D, you could immediately feed those into to M3D-C1 for plasma response analysis. You can also hook it up to various post-processing codes like TRIP3D or EMC3 Irene. So there's lots of possibilities with this. And just a final bit of motivation, I just wanted to give you an application that's made possible by this new capability, and that's using M3D-C1 to perform run-day analysis of an experiment. So last week, there was this shot that was taken in an elm suppression experiment, and somebody in the control room using OMFIT was able to make equilibrium reconstructions just maybe an hour after the shot was run. And the shot was interesting because it had a period of elm suppression when the neutral beam torque was relatively high, and then they reduced the torque by turning on a counter neutral beam, and immediately they got an elm-free phase followed by return to elming. So they made 5 total time slices using the kinetic EFIT module and sent them to me, and I was able to set up and submit those runs in a matter of minutes and obtain the results a few hours later. And it was kind of interesting that we were able to see this nice result that the peak of the resonant fields in these 3 cases decreased and moved inward as we transitioned from the elm suppressed to the elm free to the elming phase. So the actual physics result here is, kind of not the point, but it's just a demonstration that we were able to go from an experiment to a simulation result in less than 24 hours. And most of that 24 hours was taken up by waiting for the cluster to actually do my runs, the fact that I slept, and time to make this plot and everything. So, the actual computations took just a few hours, which is so it's exciting. It's an exciting thing that we can now sit in the control room and be doing analysis almost in real time. In some way.
You did this on Iris or on R6?
I did this on Portal just to for speed.
It would have been even less if you ran it on Iris.
Iris, the demand's lower, but the runs take longer, so it's a kind of a trade-off.
Okay.
But given the point is the capabilities there. Given proper computational resources, then this can go as quickly as you want. The user interaction is so low that you can automate this almost entirely from shot to result. So that's just the motivating introduction. Does anyone have any questions before I actually get into demonstrating the?
On the previous slide, you mentioned DMC3 Irene. I didn't see such a module yet in OMFIT.
Maybe it doesn't exist. I was just thinking about things that I've interfaced to outside of it. But
this is more towards the future.
Yeah, it's not. Yeah, so it's something that could get done. Yeah. Okay. Great.
I have a question about running the OMFIT on Iris. I hadn't set it up before.
Sure.
And it looks like you have to do the entire setup all over again, even if you've run it on Venus. Is that correct? You can't just use the setup you had on Venus?
Yeah, because the home directory is different. You could copy, there is a .omfit directory in your Venus.
Okay.
So you could copy that over.
Okay.
Yeah.
All right.
You can run if you want to go on Venus, you can run OMFIT there, and then you can just tell the jobs that you want to submit the jobs to Iris.
Okay.
So
yeah, because it wasn't recognizing any of the servers that I'd set up, and
right.
Yeah. Okay.
So yeah, that's the nice thing about OMFIT is that it doesn't, if you want to run M3D-C1 on Iris, you don't need to be running OMFIT on Iris. You could be doing it on your laptop or at Princeton. I could be running OMFIT on Iris here and then submitting jobs to Princeton. It's all, as long as you have the SSH keys set up properly and everything, then it all works seamlessly.
Okay.
So.
Hey, Brendan?
Yeah.
So is it set up to run M3D-C1 on NERSC?
It is not, but that would be relatively simple for me to do. I got a NERSC account for the first time a couple weeks ago, so I just need to install the auto C1 script over there, which is pretty straightforward, and then I need to come up with some submission scripts for NERSC.
So for that,
Okay. I can help you with that if you want.
Sure. Yeah.
Right. We have this Atom account, which is actually what Brandon is using for his NERSC. And actually, we've been hosting a whole bunch of codes and put them into a kind of a public repository so that people don't have to have their own version of each one of the codes that they're running. So if you do that, I think it's better that we put it into like this, code repository. And then everybody who has a Atom Unix group can run all of those codes without having to go through the hassle of every time recompiling, reinstalling, resetting up the environment. So that's probably the best way.
Sure.
And Nate, I can give you access to the Atom Unix group, and that way if you want to help out with setting that up, you can do it.
Sure. Yeah, we've got a public binary version of M3D-C1 for various versions.
Oh, okay.
We'd be happy to copy it. copy one of those executables over to your Atom directory.
Yeah, we could just
We're
link
keeping-
it or whatever.
Yeah, do a symbolic
Yeah.
link or something.
And we're keeping release versions of the code that don't change.
Yeah, no, that okay.
So I think
So since you guys
we
are
did
doing
that.
already the right things, we should then adopt whatever you're using. Yes.
So
sure.
yeah, I
Just
think
most codes and people, they're not most working groups. They're not that organized. So it's great.
Yeah, we like to keep up that appearance.
Yeah.
Okay, then yeah, that's something that we can work on. I could even start working on it later today, just getting auto C1 over there. What does NERSC use? Does it use QSub or Slurm?
Slurm.
Uses Slurm? Okay,
Yeah,
then
so it should be
I
seamless.
probably can just copy over a lot of the other scripts I have. I just need to learn the partition names and all this kind of stuff. So it should be pretty straightforward. But okay, so I sent out in advance this tutorial slide that because I want to be able to share my no machine sessions so that people can see what I'm doing. So if you have those tutorial either printed out or on hand, then you can use that. But I'm going to let's see what I'm going to do here. I need to share my what's up here. New share. Okay, so I just need to connect to the Princeton.
And we're still paused for the share.
Oh, thank you. There's that. Resume share. There we go. Can everyone see that? Yeah? Hopefully it's better quality where you're looking than from our screen.
Yeah, we can see it.
So you need to, if you're on Portal, you need to load the OMFIT unstable module. And then on Iris, I put it in the notes as well, you need to load the, I think it's the Atom/dev module. But once you've done that, however you want to do it, you just open up OMFIT. And it takes a minute just to, especially on Portal, for some reason, it's still kind of slow. I don't know what it is, but.
Yeah, it's definitely slow.
Mm-hmm. Well, this gives me time to pull up my slides on my phone. Should be useful.
Princeton lost.
I know. I saw
Okay.
2 points. I had it in the corner of my screen. Missed the last minute 3. Last second 3.
But you can believe how
Yeah, I
close
knew
they
that
were.
Notre Dame would win. I knew that.
Oh.
I just missed really put my money on Notre Dame.
Prioritizations.
So was anyone playing brackets?
I don't know.
This is really slow.
Yeah, it's
It's
unclear.
usually not like this. But plenty of time to get my slides up. I have my own notebook going too. It's not like someone else is using it. There we go. Okay, so when OMFIT opens up, eventually,
Yeah, I never used it on Portal. I don't know why it's.
I usually do. I don't have a problem. I could have done this on Iris too. That would have been fine. So there's a little screen that pops up just with some updates and everything. But so this is, I showed this before in the slide, but this is what the OMFIT, what do you call this, the console or the GUI or whatever it is. So what we're going to do is go to import the M3D-C1 module, and you want to import it from the unstable branch. So you go to File, Import.
Must be the.
I could try loading it. I could just get it started in Iris, so this is going to keep going. Yes. Once we actually get it imported, it should go quickly. Is everyone who's trying to like physically follow along, do they have any problem getting OMFIT opened in it or anything like that? I know some people are kind of new to it.
Yeah, I mean, if they're new, they're gonna get, they will have to set it up and so on. So
Sure.
so
Okay.
just,
Well, let's just move on.
just
and
go
then
on and yeah.
I can answer questions later. But so you can filter for M3D-C1. You want to load. Depending on how you have it set up, you might have multiple repositories you can take it from, but you want to take from one that has origin unstable, which you should have if it's a public unstable version release. So you just double click on M3D-C1, and it will load that module into the tree. Okay, so over in the tree now, you have this M3D-C1 tab, and if you open it up, it has a whole bunch of subtrees. It has inputs, which is empty right now, a bunch of options, which are mostly empty. Everything's going to get filled in later, and then all the GUI, all the Python scripts for the GUIs and running various things are contained under GUIs and scripts. And there's a bunch of things in settings as well, which I might drop into the settings later to show you one thing. But to start the GUI, you just double click M3D-C1. And the GUI pops up. So what we're going to do is we're going to start a new run from new equilibrium files. So you have setup type. You can choose equilibrium files or start from an existing directory, which I'll show you how to do that later. And you want to choose what machine that you're working on, where the equilibrium is coming from, whether it's D3D or ASDEX. And again, like being able to set this up pretty efficiently on NERSC, we can set this up for other machines as well. So if we want to do more on STX or EATR or K-star, eventually I'll be implementing myself because I'll be using that. So this will be pretty straightforward to do. But we're going to do a D3D run, and we need to select a G file, an A file, and then some way of getting the profile. So for D3D, that could be a P file. You can use native M3D-C1 input files. So if you already have a profile NE, profile TE, and a profile Omega, you can upload those here as well. And then Morgan Schaefer has his own format that he gives us sometimes, so that's here. And if you have other formats, that's something you can talk to me about, and I can set this up to work for that too. But we're going to load a P file. So for the GEQ disk, I can start typing where I know everything is found. Data/OMFIT. And then if I click local, because I'm already on Portal, you can do this remotely too if you have it on another server. I put some files in the tutorial earlier today. So I'm just going to choose this G file. And it has I can go here again. So I'm going to do the same thing for the A file. And you can see that the G file that I chose before has a G number.number format. And I assume that what you're loading in does have that, so that this is going to help define the working directory for for the runs that you're going to do. So I'm going to choose the A file this time, and then in that same folder I have a P file as well. So I'm going to load the P file in. The G and the A file just get stored in the tree for now, and they're going to get sent off to the server later for some pre-processing by the auto C1 script. But for the P file, I'm going to extend these profiles.
Maybe you can show where those files went.
Sure. So when I loaded these files in, these all went into the inputs file. So over here now in the tree, I have a GEQ disk and an AEQ disk file. You can double click, for example, on the GEQ disk file, and it'll pop up with a little plot of the equilibrium that you're looking at. And then the Profiles In tab now has a P file as well.
Can I ask a question about the profiles?
Sure.
So when you do a kinetic EFIT, you usually start with magnetics only EFIT, and you do profile fitting, which is mapped onto that EFIT. And then those profiles are stored in the pedestal database. and later used to make a kinetic E-fit. And then sometimes, I guess most of the times, those profiles are remapped onto the new kinetic E-fit.
Right.
And those are put into E-fit tree in MDS Plus. How important is it for M3D-C1 simulation to use the latest remapped onto kinetic equilibrium profiles rather than using the ones that were used as input for kinetic reconstruction? That might be slightly different.
It depends, I think, a lot. For example, the resonant response to 3D fields can be very sensitive to the zero crossing of the rotation profile. So if the remapping has moved the zero crossing from a rational surface to in between rational surfaces or something, then you might get very different resonant responses. I'm assuming it's a very case-by-case basis, and I don't know if that's been systematically studied for every kind of profile and everything. This tool would be an interesting way of loading in. You could load 2 different P files in and run 2 different simulations to quantify, error bars on that or something. So right now, we've loaded in the 3 equilibrium files, but M3D-C1 doesn't read a P file. It reads these text files that are formatted in a particular way. And so what we're going to do is hit the Extract Profiles button, which is going to populate the Profiles Out file. And now we have Profile NE, Profile TE. These are the actual files that M3D-C1 is going to read. But typically these only go out to the separatrix, and as I said before, we need to extend these into the open field line region. So this happens in the Extend Profiles tab.
Was the P file generated in OMFIT for this case?
This case, I believe not. I think this was I just chose this case. It's one that Rafi sent me a long time ago that I know behaves well for everything, so it's simple. But the application I showed before, all those equilibria were made in OMFIT, including the P files, and those behaved almost better than this one does.
Is that the preferred way to do it then?
You can do it any way you want. However you have, you're in control. So if you have, however you have a G and A and a P file, or a G and A file and then profiles somehow, unless it's a different format, then you just need to contact me and I'll figure out a way of allowing you to read those in. But it's completely, however you want to make your equilibrium, M3D-C1 is going to give you the solution for whatever you put into it. So if it's a bad equilibrium, it's going to be a bad result, a bad result. But that's completely up to you how you want to do it.
All right.
Do you benefit from a higher E-fit resolution?
No, that doesn't matter. The M3D-C1 grid is a much higher resolution than anything E-fit is going to produce. And it needs to be remapped onto the equilibrium needs to be recomputed in the M3D-C1 finite elements anyway. So we actually just read the P prime and the FF prime profiles typically from the G file anyway, and then we're gonna redo the Grad-Schifrano solve. There's another I don't know, for the Nate, you might be able to respond to this for the fixed boundary simulations. Does the E-fit resolution matter because that's actually reads the psi from it, I know.
No, I don't think it matters too much. Psi is very smooth even on the very lowest resolution E-fits.
Okay, great, yeah, so.
Okay, thank you.
Okay, so after we've extracted the profiles, we go to the Extend Profiles tab, and typically we just extend the density and the electron temperature. If for some reason people want to extend rotation as well, I could easily add a tab to do that as well. But under the density tab, you see it's going to do a linear tangent fit to this to the profile that you give it. And so you have the minimum value that you want the density to get to at the edge, the innermost point that you want to fit to this profile. Then you have the psi n value that you want to extend to, so that's something greater than 1. And then you have a center and a width for the tangent part of the fit here. And so you can change all these parameters however you want. These are some common defaults that we use, or I use at least.
Is that minimum value in like 10 to the 18, or is that?
10 to the 20, I believe. Yeah.
You could probably write the units.
I could. Yeah. I should. Notes. Sorry, guys. 1 sec.
So your default value is 0.01. What's the range that will be not causing problems in simulations?
That's a good question as well. It's something that I hope to actually kind of study with this tool as well, since we can do I could iterate on this. I think the temperature is typically a more important one because you need to get to a really high resistivity to make sure you don't have currents flowing in the vacuum region. Yeah, I don't know. I would say that the 0.01 is kind of almost a maximum that I do.
I just tried it at 0.02 and it failed.
Okay, yeah, that's fine. So
Pretty much got just
so the fits may fail. Yeah. So hold on. Units for extend. Okay. So let's just try it with these defaults. The last one I didn't mention is a Cyan to smooth from. So there's a possibility that maybe your fit doesn't exactly match the data inside so well. And so you can choose, maybe from 0.99 to 1, you want to smooth between the two, and so you get a smoother profile. But this example doesn't really demonstrate that. But anyway, I'm going to hit Extend Profile NE, and it pops with the defaults, and it pops up a plot here. The orange dots show me the input data that went out the side of 1. And then the green is kind of underneath all of this because it's a good match. But then the blue is what the profile that I'm going to give to M3D-C1 looks like. And you can see it gets down to about 0.01. Here you can see the units 10 to the 20th. I put them on the plot at least. Over in the console, it has some printout of what the final fit parameters are and tells you what the minimum value was. So I wanted 0.01 and I got to 0.011, so that's good. So everything looks good with this fit. So I'm just going to hit accept profile NE extension. Now I go to the electron temperature tab, and I have basically the same parameters, except I want a much lower value. This is in keV, so I want 0.1 eV as my temperature in the vacuum quote unquote region. So when I hit profile TE, I look at it. I can see even from the plot that 0 is not at the bottom. It looks like it kind of drops down and comes back up. And then if I go over to the console, it printed out a little warning letting you know that the minimum value of the temperature went negative. So I have this profile would have a negative electron temperature. That's no good. So I know that this isn't a good fit. I need to change something. And so I know for this one that if I change the minimum Cyan that I'm fitting from to 0.9, whenever you change something in these GUIs in M3D-C1, you typically have to, when it's green like this, that means you still have to press enter for that value to actually change. I hit extend profile TE again, and now I'm getting something that looks good. And I go back to check over here, and the minimum value is no longer negative. It's 0.001. So that's good. So I can accept this profile TE extension. So now I've extended the profiles that are going to be used at M3D-C1.
So this says fitting range 0.95 to 1, but you're extending it to 1.1.
Exactly.
Does it also fit? Can you change that range to fit deeper in?
Yeah, that's exactly what I just did there to make this work.
Yeah,
so
okay, that's what I thought you were doing.
Yeah,
okay.
so I
could
changed.
go all the way.
I could go. Yeah, I could do. Well, now that I hit accept profile T, I'm not sure
Yeah,
how it'll
that's
be
fine.
saved, but
you could essentially shift it as well.
Yep, you can play with these parameters as much as you want until you get something that looks good to you, including if the. Let me just see. Let's extend it out to 1.2 real quick, just to take a look. So if this blue line
Mm-hmm.
and the orange line, or the orange dots, sometimes you get what this does is it takes the data that you've given it
All right.
out to as far as you have, out to 1,
Mm-hmm.
and then it's going to use the extension from there. So if the fit isn't great, sometimes you can have kind of a discontinuity
Mm-hmm.
right at the boundary,
Okay.
and that's where that smoothing function comes in. So you
Alright.
could smooth between the two to get rid of the discontinuity. But I'm happy to, if people start having trouble with that, I'm happy to talk to them about it as this goes on.
Because sometimes you might want to change the temperature on the separatrix by just shifting the curve a bit.
That could be trickier because it's going to try to. That you would probably want to do with the initial file that you're putting into it,
Just
not
go back to the P file and do that.
and do that there, and then go into here. This is more for just taking the data that you start with and making it go farther out
Right.
to some low value.
Okay.
Okay, I've already accepted the profile that I want, so I'm just going to ignore that for now. Anyway, so now we've pre-processed the equilibrium files the way we want. We have the appropriate profile NE, TE, and profile omega file. So now we need a C1 input file to actually run M3D-C1. So this is, again, just that Fortran name list. So if you click on the Setup C1 Input tab, there's you have two options. In this case, you can load the default one, which will just go to the server to the templates that I have set up, and get a C1 input. I call it C1 input base, and because it's each kind of run that Auto C1 does is going to change the C1 input file slightly. You can also load an existing C1 input base. So if you've done another M3D-C1 OMFIT run and you have a C1 input file that you want to reuse, you can do that, and then it'll ask you where to find that, either on the local or the remote server. But we're just going to load the default C1 input base file. So I select that one, and I hit load, and it's going to, over here now, it's going out to the server, it's getting the C1 input file, and so now it's loaded it into the tree. And that is now under inputs as well, C1 input base.
Can you expand it just to see it?
Sure. So the C1 input base has the input name list, input NL, and it has all the parameters that are inside of the C1 input file. This default one has some of them set to none or just blank. For example, the toroidal mode number, because we haven't defined what toroidal mode number we want to do in these simulations yet. So we're going to set that up later, and Auto C1 takes care of making sure that the C1 input file is complete when it's actually doing the runs. So now if we want to, if you want to change a parameter, you can do that here as well. So I have 3 different ways of doing that. There's common parameters that can be changed a lot. For example, I can select if I want to have equilibrium rotation in my my profile. There's 3 different options for that. I can say the input rotation profile that I'm feeding it, is that the electron rotation, the E cross B rotation, or the ion rotation. And then for these are the names in C1 input. I think I put some descriptions over here. So AMU is a value of the kinematic viscosity. Then M is the density diffusivity. You can change the ion mass, E effective. So this is what I call the physics model parameters. You can change parameters for the M3D-C1 scratch Refranov solver. For stability calculation, you can change the number of time steps that you want to do. For 3D response, if you want to have a finite frequency of the response instead of 0, you can change that here as well. So these are kind of common parameters that one might want to change in these simulations. If you want to get more detailed, there's an all button, which basically just takes this from the tree over here and puts it right in here, and you can edit everything as you want. It's very long, obviously. You could also edit it directly in the tree if you wanted to, if you're familiar with that. Or if you were linking codes together, you could imagine writing a script that would change values in the tree as you were doing this. I also give you the option to do it by a key and value, so I can tell it what some other parameter, maybe that's not included in the C1 input file that you know that you want to add into M3D-C1. So, I could change some parameter named high to some value called there, right? And then I would click add key value to C1 input, and it would add that to the name list. But we're not going to actually add that in because that would not work well. So we're just going to use the default parameters for now, but this is a useful interface for changing all that. So now we want to select what calculations we actually want to perform with M3D-C1. So that's in the Select Calculations tab. And I give you 3 different options here. I can do an equilibrium calculation. So if I just want to see what the equilibrium looks like in the adapted M3D-C1 mesh, you can do that. So sure, let's add that calculation on there. So it shows up here. It says equilibrium. So the left-hand side here is all the calculations that you've already added, and then these are the ones you actually want to run, because I can remove that if I decide, I actually didn't want to do that one. I can remove it from the list of things that are actually going to run over here. And then I decide I do want to run it, you can add it back. It says none because it doesn't have a toroidal mode number for the equilibrium, and it doesn't have a single or 2 fluid option for the equilibrium, so it just, I don't have any other, I don't know. That's just it's some tuple that OMFIT is processing that way.
If you put it as an empty
String?
string.
That could be useful. Okay, maybe I'll change that, but that's not too important. But let's say I want to do a 3D response calculation. So I change my calculation type to 3D response. When I do that, now I get the option to set a toroidal mode number, say toroidal mode number of 2, and I can choose single or 2 fluid. So I'll choose single fluid and I add that in. Now it says 3D response n equals 2 single fluid calculation. So that looks good to me. Now I can run. Everything's been set up properly. So I just choose whatever server I want to run on. So I can set it on Portal. Or for now I have Iris or Saturn as well.
Can you do more than one toroidal mode number at a time? Or do you...
Sure. So I could add in, let's say I want to do n equals 3 as well. I would just hit add calculation, and that would do a n equals 3 calculation as well. Yeah.
Okay.
I get an error if I do it on Iris. I can show you later.
Okay. That's interesting. Yeah.
I mean, it's some module conflict, I think. It's not.
Oh, yeah.
I have purged everything and tried it, but it says that there's a module conflict.
Okay, we can look at it later.
Okay.
But I'm just going to remove that one now. So we're just going to do these 2. So I'm going to say I want to run in Portal, and then it asks you for a run ID as well. So this is just a unique identifier for this run to stop you from overwriting any other run that you might do. So I already have tutorial in there, so let's call this tutorial live. I'll call it live. Sure. And again, it's green, which means it hasn't actually been changed yet, so I hit enter, and that changes it. So now, before I hit run auto C1, you might want to know where is this actually going to appear. So if I go into the tree, to settings, remote setup, there's a working directory here. This working directory, I can just X out of this for now. I'm just going to close this for now, but I can open it later without any problem. This working directory, if I hit print, shows me that it used a /p/tsc. I have a Lyons folder, so it's going to run there. And then it will create an M3D-C1 data OMFIT. This is a safety thing. Any folder that OMFIT tries to run in has to have, in all caps, OMFIT somewhere in the thing. That's to stop you from overwriting your entire directory structure or something. And then I'm doing a D3D run, so it filled in D3D for me. It filled in the shot number, 158103. It filled in a time, 03796. That came from the format of the G file that I mentioned before. If I can scroll up, that's here. Yeah. And then it has my run ID live. Now, if I change, I can open up the GUI again. If I change from Portal to Iris, that's going to change my working directory. to an M3D-C1 results directory with Lyons BC, and then after that, it's all the same again, data, OMFIT, and D3D, On Portal, if you don't have a TSC account, so if you don't have that /p/TSC, then it runs it in the OMFIT directory as well. But you can always look in, I think when you do the run, it'll tell you what the working directory is anyway, but you can look in the tree to see what working directory you're in. And you can always change it if you needed to for some reason. But we're going to open this up again. And I want to run on Portal. So I hit select Portal, and then I hit Run Auto C1. So now I get this execution tab that's telling me what it's running. It's running this script that's going to set up your modules, hopefully properly. Apparently there might be some conflicts that we need to look into. It opens up an SView, which is this GUI for looking at your runs, your Slurm runs, available on both Portal and the G8 clusters. So I can scroll down to the bottom. And now I can see that it submitted 2 runs to me to the Cruscal queue. One of them just completed, so that was mapping the EFIT to the uniform mesh. That's really quick. The equilibrium will take a couple minutes to respond, to update. Once that's done, it's going to actually plot some sanity checks for you. So it's going to pop up with a Python plot that shows you the shape match between the original EFIT and the new one that you have in M3D-C1. It's going to show you the density, the temperature, the electron temperature, and the ion temperature on a 2D mesh, so you can see if you have negative ion temperatures in a big part of your equilibrium, which happens sometimes if the P file isn't, if the P file hasn't been remapped, then maybe you could have NE times TE is higher than the G file pressure, and so you get a negative ion temperature to compensate for that. So it's going to pop up some common checks that you want to look at, and it also saves that file into the folder. But while this is running, I wanted to show you what the directory actually looks like. The whole run will take about, I'd say, a half an hour before it's actually going to submit the jobs to the actual calculations that you selected. That's doing all the setup runs, adapting the mesh, and all that kind of thing. That can change depending on cluster usage and whether you're in Iris or Portal and all this kind of stuff. But it takes a little while to run. But you don't have to touch it. It's doing that all in the background for you. So I'm going to go to I'm running in something called Live right now. And so it's doing things right here. But I have a complete one from yesterday that I ran called Tutorial. And I just kind of wanted to walk you through this. It's using a consistent directory structure so that you can go back to later and easily be able to see what's going on. So it does that mapping of the equilibrium on the uniform mesh in this uni-EFIT folder. It does the recomputing the equilibrium on the uniform mesh in this uni-equal folder. And that uni-equal folder actually has an iteration number inside of it as well. That kind of harkens back to the days where we used to have to iterate on the coil currents in M3D-C1. Typically that's not needed anymore, so it just does one iteration, but I kept it around just in case something in the future calls for us needing that again. It then computes the adapted mesh in this RW1, so resistive wall adapt folder. So RW1 adapt. This run will stop once it produces this adapted 0.smb file. That's the actual mesh file that we're going to use. And then the actual the equilibrium calculation I asked for is in this RW1 equal folder. And then I asked for an n equals 2 response runs inside the n equals 2 folder. I have an upper and lower iCoil response calculation that's been run. There's a few other things in here. You can see that these OMFIT run command.sh and OMFIT runs auto C1 Python. These are scripts that OMFIT is using to actually do these computations. There's a C1 input base 0 file. So all of these files here have some unique number appended to them. So that if I were to come back to this folder and say I want to restart a run, and I'll show you how to do that in a minute, and I send it to this folder again, it doesn't overwrite anything. It's just going to now it'll have scripts with an _1. It'll have a C1 input base with an _1. This all also goes into so I can actually show you from a previous run I've done what that looks like. So if I go to portal start, I should have it. Hopefully. Yeah, so here I did 2 different runs. I did one run that did everything to start, and then I wanted to do some additional calculations. So it made these _1 files, and then in this run files folder, it maintains a record of all of those, and it also has this run directory.txt file that tells you that iteration 0 was run on Sunfire, which is Portal, with Portal Server. Oh, that's interesting. So this is the name of the folder that was originally run in, and then it was restarted and run with a new run ID. So if I can start from an existing folder and then run in a new folder, and it will maintain a record of where things started from. So if I'm doing this 100 times, you know everything that got you to this point.
Mm-hmm.
Okay, so we finished the equilibrium step of this run now, and so now this Python figure has popped up. Here's the shape match, and we can see that the original EFIT is in black. The recomputed equilibrium is in blue, and there's a good shape match basically everywhere, so that's good. The density is positive everywhere, that's good. The electron temperature shows some noise outside the separatrix. Once we adapt the this just comes from user experience, but once this kind of noise isn't too concerning because we're on a pretty coarse uniform mesh right now. Once we adapt the mesh, that I can tell from this that's going to go away. That's a good thing to check always. Same thing with TI. The bigger problem is if you saw like a pretty consistent area of blue somewhere, that tells you that your profile is actually negative and that you need to go back and change some parameter. But everything looks good, so I'm confident that this run's going to succeed, so I can just X out of that. But that gets saved into this equal_check.pdf file as well, so you can always go back and look at it if you want. So now it's running the M3D-C1 adapt run, so it's adapting the mesh, and this is going to take a while, so we're not going to sit here and wait for that to run. But yeah, so that's kind of the basics of how to get a new M3D-C1 run going. Are there any questions before I go on to a couple other quick things?
So if your equilibrium is too bad and you realize that, how do you stop it? Or you do like first make a run where you just find the equilibrium again, and then you put in all the n = 1, 2, 3 calculations?
Yeah, so stopping it, I haven't made a great way of doing it. So inside with OMFIT, I can always hit abort, and it will stop the scripts from running on the remote server. This actual run here will keep going.
We just added with Gregory. We just added the ability to add buttons to that. If you go back to OMFIT, there is the thing going back and forth.
Mm-hmm.
So you can add a button that says, delete run, and it will go and do QDEL.
Oh, okay.
So or scancel, whatever.
So there will be a kill remote button that will be sending a term signal to whatever you have running remotely.
Okay.
So if that's something waiting for your submitted job to finish, in the QPrint that's doing exactly that, in whatever scripts folder on OMFIT, there will be a trap for the term signal that will catch the term signal.
Yeah, but
and
he's not.
submit an S cancel.
Yeah,
Yeah,
no, it's not
he's
that.
not doing
It's Slurm jobs that need to get, get canceled.
Yeah. But it's okay. I think we too much detail.
So we could set up necessary, but I can. What's up?
We'll talk about that.
Okay. So, but I could always go here and hit cancel if I wanted to cancel this job as well, if I knew it was failed, but I'm not going to do that. So,
Can I ask a question on the setup?
sure.
I will just go back to the select calculation tab.
Sure.
When you do 3D response, you put in the throttle number. I probably missed it. Where do you specify all the coil currents and?
So this always assumes these are linear calculations.
Yes.
So I always assume that there's 1 kiloamp of coil current in them, and then you can define the
So
coil currents yourself post processing.
This is just the I coils.
Yes,
There is
and
no
it uses
way-
the M3D-C1 model.
Yes,
But I
understand.
haven't set it up to use Pro G files or anything like that. We could
But
get that working too.
How difficult will it be even give the ability to change the M3D-C1 internal coil model to specify R&Z locations of the conducting segments?
I mean, M3D-C1, the way the coil model is defined is just, where am I? If I go to equals 2, so there's an RMP coil.dat file that gives the RZ location. This is for the upper I coil.
Okay.
And then there's an RMP current.dat file.
Technically, that can be put here into the.
It could, yeah. If that's something that's going to be used, if that's something that's going to be done routinely, then that's definitely something that we could do. Yeah, we could talk about that more.
Sure.
And so here it's telling you
this is
just
just-
1 kiloamp of coil.
This is hardwired for D3D right now, for the D3DI coils.
Well, yes, it is. But if I went and selected,
A different machine.
if I selected ASDEX here,
Uh-huh.
it has the upper and lower ASDEX coils hard coded in there as well.
I see.
When I do K-star, it'll have the 3
Uh-huh.
coil sets hard coded in there.
Okay.
And it's
And- Go ahead.
it's currently hard coded so that the upper and lower coils have the same phasing, so that the current is the same. in
Yep.
both
So
of them.
it'll be even parity in both of them, but they're separate. And the idea is that these are complex linear calculations, complex in a mathematical sense, and so they can be. You can combine them with an arbitrary amplitude and phase. Combine the two with an arbitrary amplitude and phase, and get odd parity by just
What I'm
flipping the
guessing
coil
what
curve.
Bob's asking is right now when you do a solution, you assume that both coils are on, and you get a solution from both.
I get a separate solution for the upper coil and the
Okay.
lower coil.
That's
okay.
So
That you can linearly
It's always gonna
superpose.
do-
Yeah.
it's hard coded to run both at the same time, just
Okay.
because usually most people want that, and it makes life easy. So it may be if you just wanted the upper coils, it'll do an extra run for you, but that's
Yeah.
that's
No,
the
that's
computer's
okay.
problem. That's the
But-
computer's problem, not yours.
Just as an extension, it'd be good to add here the option to read the probe G fields.
Yes, I agree. I just haven't gotten around to that. I've been kind of modifying this as I've had to do something, and no one's asked me to do a probe G run in a while. So
Well,
Um,
I've asked. Right now.
yeah, there you go. So any other questions? Cool.
Brendan, after you get the adapted mesh, could you get a picture of the mesh line?
Yeah, so let's go. Yes, but okay. So I kill that adapted mesh run, so you never get a C1.h5 file out. So once it does the calculation that you've done, you can definitely look at it, and I can show that here. So in the post-processing tab that I have here, I can say select a directory I want to look at. So M3D-C1, data, OMFIT, D3D. and we'll go to the one I did last night and say, okay, I want to look at what's, the run that was in this equilibrium calculation I did. So there's a C1H5 file inside of this folder that I selected, and I hit OK. And then I can go to the plot tab, and I can say I want to do an IDL command. It tells me that it's going to, in IDL, it's going to define this dir1 as this thing here. So I can click on this triple dot, just means I can do a multi-line command if I want. So with that, I could do a plot mesh dir1 C1 H5. I don't know if there's anything else. I don't use this command too often. Is it file equals? Does anyone know off the top of their head over there?
No.
No? Let's try that. I'm going to hit plot. So it's done so now you can look at the mesh there, and then I can go back and I can say, oh, that's too much. I just want to look at R range equals 2.0 to 2.25, and Z range equal to minus 0.25 to 0.25, and I want it to have the right aspect ratio. So update, plot that again. Oh, maybe it's X range for this. Sorry, guys. Not a command I use very often. Yeah. But the point is, you can do this. You can enter any IDL command that we typically use with M3D-C1 here, and you can see the mesh there. So that would be the way you would do this through OMFIT right now. You can also just go use whatever tools you want to look at before. If there's another way that you want to do this, I could update it, for example, to not kill that RW1 adapt run right now, so that it would complete it, and then once it was done, I could update it so that it made a mesh.pdf or something like that would print out every time as well. But that's not something I look at too often myself. Maybe that's not a good thing. But yeah, I'm open to, as long as there's interest in this and people are using it, I'm open to continuing to develop it and support changes that people want. I think now that I'm kind of I'm letting other people use it, there'll be some constraints on what I do, because I'm going to want to keep backwards compatibility so that you can go back to past runs and look at it there. So directory structures and that kind of thing, I might want to keep with some level of consistency, but we can work with that as we go. Does that answer your question, Steve?
Yeah, it does.
Okay, thank you. You can also, I have it set up to use some Python routines that I written for M3D-C1 as well, but they're incomplete compared to the IDL routines right now. So doing the post-processing here requires some expertise in how M3D-C1 gets post-processed before. I started making a GUI to allow users to do this automatically, and that just turned out to be, I think, a lot more trouble than it was worth. The one thing I do plan on adding, eventually there's going to be a drop-down menu here, so you can select different kinds of plots that you want to make that are common. For example, if I want to plot the pressure or something like that, they'll have a plot field pressure. And then you can modify it from there to fit your specific needs or something like that. But I haven't gotten around to actually, that's pretty straightforward. I just haven't gotten around to doing it yet. I think the only other thing I wanted to show everyone, so I'm just going to close out this and the IDL session since it's not taking up resources, is back in the Setup Equilibrium tab. Let's say this whole run, a run's completed. So, and now I say, oh, I did I did an n=2 run, but I really wanted to do n=3, or I want to also do it for 2 fluid or something like that. So what I can do is go to Setup Type and select Existing Auto C1 directory. So this tab changes now and asks you what's the Auto C1 directory you want to run in. So I'm going to go to Local, and it's already selected this tutorial run that I did yesterday. Let's say I want to add something to it. So I clicked OK. So it's it's loading that in, and you have to, with this one, I can't just type in the directory even if it's local, because it needs to know what server you ran it on. So you have to either use the local tab or the remote tab. And then I can say, do I want to do the runs in the selected directory, the one that I'm already working in, or do I want to do it in a new directory, in which case it's going to copy a few additional things over so that it can send those off to the new directory. And then it asks you what server you're going to want to run it on, and give it a new run ID as well. And what this is going to do is it's not going to redo some of the runs from the beginning. It's not going to redo the equilibrium run, the mesh adaptation. It's just going to use that from the existing directory and do a new calculation. But for example, I'll just do it in the selected directory. So it's going to rerun it in that tutorial tab. And I go to Select Calculation. I'll remove all because I don't want to redo ones I've done already. And let's say I want to do a 2 fluid run. I'm going to add that in. So now it says we're going to do a 3D n=2 2 fluid run. I hit Run Auto C1. This will be really quick because it's not waiting for anything to finish. It's just going to submit the jobs. And it's done. And so now I can go back to that tutorial tab. Where am I? Sorry, guys. So now you can see it's added in an _1 for the new runs I've done. And if I go into the n=2, it now has 2 fluid runs, fewer files in it because the runs haven't actually started yet or anything like that. But now these are submitted and ready to go. And then I'll just demonstrate how it works if I went to a new directory. We'll call this tutorial 2. And for this one, let's say I want to do an n=3 stability calculation. So I didn't show that before. You can do stability as well as the same options, right? So now I'm doing stability for the n=3 with 2 fluid effects. Add that in. When I hit Run Auto C1, again, it's going to go to the server, send out everything it needs. And it's already done. So now, in this same thing, sorry. So now this is my new directory structure. It started with iteration number 2, because it's trying to maintain what you've done before. If I go into the run files, run directory, it tells me that iteration 0 and run were run in this folder on Sunfire. And then iteration 2 is now, iteration's not the right, index number 2 is now this folder here. It copies over the RW1 adapt folder, so it has the adapted mesh. It copies over the EFIT, so it has all the input EFIT. And then in the n=3, there's a 2 fluid stability run folder that's sitting there waiting to run as well. And I can do this on another server, so I can start, let's say Princeton I was doing work on Princeton and it's having a really bad day with someone else using the cluster. I could change this. I'm not going to do it, but so I set it up so that once you do that, it's the directory that you're now running in became the selected directory. That's to stop you from overwriting what you've done. You have to be careful that the run ID that you give it is a unique one, because if it exists already, it's going to overwrite what you've done before. So just be careful about that. But if, again, I went to a new directory, So essentially, these directories are self-describing. And so, but now I could go to Iris and tell it to go do something, and it would do these same things on Iris now. So I think that's everything I had. Been talking for over an hour, so I hope that made sense. I don't know. Has anybody actually been following along, trying to do it, or have people just been watching?
No, I would try to do it, but I got kicked out at some point. But it totally works out fine.
It makes sense.
No.
Does it make sense? Does it seem kind of intuitive and everything?
I guess I just have to get more familiarized with the structure that's output and look at the details.
Mm-hmm. Exactly. Yeah. So, yeah.
So once you get the solutions and you want to do some plots, can you do that inside OMFIT, or do you have to go to
You could do that with this post-processing tab.
post-processing? Okay.
This post-processing tab lets you select the directories that you want to plot, so that way you have easy access with a certain variable name here, and it'll tell you all the. So if I went to the whole
Okay.
tutorial equals to, for example, so I've loaded in a couple of them now, and so it tells you this one is dir 1, this one's dir 2. So now you have to be familiar with the Python or IDL routines that are typically used. I'll make a drop-down menu to try to simplify it a little bit, but it requires some level of expertise to know what you're doing.
All right.
But now I can use these variables in this script now to
I see.
say what I want to do.
So that's basically what you were doing to do the equilibrium.
When I was showing
grid.
yeah, exactly. Right. Or when I was showing the mesh, when Steve was asking about the mesh, that's what I was doing.
All right.
I also, the other thing that can be done is this. This could be linked up to Trip3D.
Mm-hmm.
The directories where they are and everything now, so you could go and do that in the OMFIT tree as well with the Trip3D module or something.
Yeah.
So.
Okay.
The one thing I don't do typically is I don't really pull anything back to the OMFIT tree. So OMFIT has this inputs tree here, which is everything that's going to get sent to the server that I'm running on. It also has an outputs tab. I've elected to not pull anything back into the tree when you do these runs. The H5 files are like half a gigabyte worth of stuff, and I think it's just worth keeping it stored wherever it is, not in the tree itself. The one thing that this does do, I should note, is when I'm doing the post-processing, I can select to run on a remote server that I want to analyze.
Mm-hmm.
When I click, it'll come with the box. I tell it the name of the folder and what server to look on and everything. When I click on plot, if I do that, it's not going to try to plot remotely. It's going to see if whatever directory I've given it is local, like if that exists. And if it doesn't, it's going to go to the remote server, fetch it, rsync it back to the local server, and it's going to add to the run ID like underscore server name underscore, so that that's going to be saved locally. It's not going to overwrite anything else, and so now it has a local copy that it can that it can plot from or something like that. But.
Yeah. So, for instance, you could pull up the surfnN module that Dimitri wrote and run that on one of the H5 controls files. Yeah.
Yep. Yeah, I mean, right now the H5 file isn't in the tree. If you wanted to go and fetch it, you could.
Mm-hmm.
That's simple enough.
Okay.
But any other questions?
So it seems like one of the potential advantages of this automated stuff is doing parameter scans and uncertainty quantification and that kind of thing.
Yep.
So do you think it would be possible to hook this into something like VariPed, or just have it set up to do a run over a scan of any kind of parameter that you want, like the viscosity or resistivity?
Absolutely. So that's everything that's in here is kind of the GUI is just an interface for what's going on in the tree. And so like when I click the run when when I click this Run Auto C1 button, all it's doing is going to scripts, and it's doing this. It's running this Run Auto C1 script. So if I wanted to do a parameter scan, let's say, okay, so here's my C1 input base file. I've got kappa T, right? So this, you have to have some experience using OMFIT. I'm not going to go into the details. If there's a strong desire to learn more about it, at Princeton, I think Orso would probably be happy to eventually do a tutorial for everything. But just as a quick example, let's say I want to change kappa, I want to do 1E array. So this is all in Python. Array 1E minus 8, 1E minus 7, 1E minus 6. And then for K in K, I'm going to set, real quick. I'm going to set this input nameless parameter equal to that value. And then I'm just going to, for now, just to show you, let's do 1E minus 5, print. So when I run this, you can see that it changed to the last value in the tree. Oh, I shouldn't point with my finger over there. So, this went through and it changed it 1, 8, minus 7, minus 6, minus 5. But what I could do is just add in, if I go back to, this. So that's the script. This is the script that actually runs it. I could do where that script is in the tree, .run, and I could run this little script here, and that would run auto C1 for all those different kappa T values. And so it would do this serially right now. So it would wait for one run to finish before we do the next. But if you went overnight, then it would just do this, no problem. I think there's a way of doing this in parallel as well. But
so
I'm
you
not.
use a .prun,
Mm-hmm.
and then you will have probably whatever array as a parameter of the prerun, saying kappa T is equals array 1, 2, 3, 4, 5.
Sure.
And then you will have a pre-run, which is just an instruction of what you have to do before you start the script.
Mm-hmm.
And will be getting the parameter that each copy of your process will have and put it in the tree.
Sure. So
That way
yeah,
you
the
can just
details I
gather
think.
data, but
Yeah.
it should be. There might be some issues depending on what you're doing.
Yeah. Yeah, but the point is that you could do this in parallel as well. So it would run all of them at the same time. And it doesn't have to be as simple as changing a single parameter. When I did that example I showed before in the control room, I made a little script that just went through the G files and loaded in, instead of loading it from the G file from the GUI, I just I said this equals, and then there was another kinetic EFIT module up here that had the G file that I needed, and so I just pointed it to there. And so you can set up scans like this pretty easily. And so we're planning on doing that. I'm working with Orso, with Tom Osborne, a little bit with Phil Snyder. We're trying to do and Todd and Carlos. We have a whole bunch of people here trying to do a predict first triangularity scan study for upcoming experiments on D3D and K-star and ASDEX as well. But do some simple things where within EFIT we modify the shape just by itself and run M3D-C1 in different shapes. I've actually done that already. That was really easy. But then we want to self-consistently change the pressure profiles as the shape is changed because the pedestal stability changes. So we're going to couple in variped and or EPED to this as well to try to predict when we change the triangularity, what's the pressure profile going to be what's the bootstrap current going to look like, and then from there, what's the plasma response going to look like. And so before these experiments even run, we're going to try to have some predictions for, what what Elm suppression thresholds might look like and that kind of thing. So that's, really, really simple example there, but this can get as complex as you want. Cool. Any questions? If not, then I think we'll end it here. I'm sorry.
Just maybe I missed the IDL commands. Those are related to the IDL tools that you have.
These are things that Nate has written,
Yes.
and there is documentation on that I can send out.
Okay, but maybe can you just put in a bunch of default?
Yeah, I said I'm going to do that. Yeah.
Okay.
That is in the plans.
I
Yeah.
missed that. Sorry.
Yeah, no, it's okay. So I will make a little drop down menu with examples. For example, I might have an example of how to plot the pressure. You might need to know what the variable names are if you want to plot the current instead, how to change from pressure to current or something like that. But it'll get you the basic command, and then.
But going from here, it's easier than just to do a GUI with the button say plot P. This is the range.
I think so.
And then
I tried
generate
doing
the command.
I did that a couple weeks ago, and I have that saved and everything. And it's just there's so many branches for different things you can do that it took me a day to make one command, and then I started working on another one, and I said this is the amount of time it's taking me to do this. Somebody else can learn the basics of these, either the IDL commands or the Python commands, and go from there. So I just gave you an interface for how to do that in the GUI. But I'll send out. I'll send out the a link to Nate's documentation for the IDL routines as well that people can use.
Yeah, that'll be good. One thing that I like to do is plot those total BMN radial profiles.
Mm-hmm.
And I know Nate has an IDL tool, but every time I use that, I find it confusing because it's kind of hard to distinguish the colors and all that stuff.
Okay.
So I prefer getting the text file and plotting it in MATLAB.
You can do that too. You could just use the IDL routine that will, when you run that IDL routine that makes the plot,
Right.
you just add I think it's BMN CDF equals a file name,
Right.
and then it'll make the plot for you, but it'll also produce the
It'll
file.
dump the file.
And then you could go to the directory there and plot it however you want.
Okay, that's good.
Brendan, you might even consider adding that post-processing step in automatically for the response calculations.
I thought about doing that. Yeah.
Yeah, because you basically always use that data.
It's true. Yeah.
I think to just have it automatically done and automatically output the data and have some tools for disputing it.
Yeah. Yeah, it's a good idea. I have to think about the details of how to do it. That should be easy. Default. So I could do for the 3D response, the BR and the BMN plots,
Right.
and then for the stability calculations, I could plot the eigenmode and the kinetic energy time trace or growth rate stuff as well.
I find that very useful to be able to see that.
Sure. No, that would be helpful for me too if I didn't have to go, and that would have made, if I do that, then this will go even faster. What I did in the control room the other day, that would have been done already basically. So, cool. Like I said, as people are using it, if they have problems, you can contact me. If it's something on the OMFIT side, feel free to go on the OMFIT GitHub and open up an issue and just at me, and I can work on it from there. If it's something that's, on the M3D-C1 side or something, you can email me as well, and I can work on it from there. And then as you're using it, if something's confusing, feel free to contact me, or if you want some new feature, you can contact me about that as well. I'm happy. Like I said, if there's interest, I'm happy to keep developing this as much as possible. In the meantime, I'm just going to develop it as I see useful until others start bugging me about it. So,
Sounds good.
great.
Thank you very much.
Of course. Yeah. Thank you guys for coming. Appreciate it.
Okay, thanks, Brandon.
No problem. Thanks, Nate.
So were you recording? Was Orso's?
Orso's recording.
Where? This is no. Doesn't seem like.
I think he was recording with a.
Oh, I see.
I don't know how that works. I've never worked with it before. So.